Okay, so we're here now with Hiroshi Mizuta, who just gave us a very interesting presentation this morning on a couple of topics. We're going to get him to tell us a little bit more about using helium beam for lithography. Mizuta Sensei is at JAIST, J-A-I-S-T, Japan
Advanced Institute
Advanced Institute of Science and Technology.
Yes.
But he's also associated with the University of Southampton in the UK, and he seems to spend some of his time in England and some of his time back here in Japan. What are your main interests? Is it mostly two-dimensional systems, or just in general? What kind of things interest you in your group?
In general, two-dimensional materials, but for device applications.
Yes.
Until 5 years ago, I was completely silicon nanoelectronics guy, so single electron transistors and also NEMS based on silicon.
Yeah.
But 5 years ago, I gradually moved to graphene.
Yeah.
And at the moment, now maybe 70% of my staff students working on graphene-based NEMS and nano devices.
Yeah, I was very impressed with your talk. In particular, it has a very had a sense of the importance of applications and
Thank you.
And actual products that will come out of this type of research.
Yes.
Today, Dr. Mizuta told us about his work in nano-electromechanical systems, so-called NEMS. But also, I wanted to ask him to tell us a little bit more about the other topic, which was using helium beam lithography. So as you know, electron beam lithography is a very common means of patterning devices and writing very fine lines. So tell me about how you came to be using helium beam lithography, and maybe tell the listeners a little bit more about it from a sort of fundamental, basic point of view.
Sure. Yes. As everybody knows, we've been using electron beam lithography to make the silicon nanostructures and also graphene nanostructures. And so I did the same thing, when I started, graphene research. But when we tried to make the really small structures, like 30 nanometer, 20 nanometer, and down to 10 nanometers, and I found conventional method based on the electron beam lithography is getting very difficult. Back to 2009, we bought a new microscope. It's called a helium-ion microscope in Southampton. And we enjoyed using that toy as a microscope.
Yeah.
And the big difference between the electron beam system and the helium-ion beam system is of course, helium ion is heavier than electrons. So, quantum mechanics says, the Broglie, length of the helium ion as a quantum wavelength, is much shorter than electron beam.
So about massive
about 300 times shorter. Therefore, in a microscope, when the beam pass through the aperture, usually an electron beam has a diffraction. But in the case of helium ion, the diffraction is very, very small. Therefore, we can confine helium ions within about a diameter of 0.5 nanometer. So it's really the focused ion beam. But helium is very light compared to conventional gallium ions. But still, it's ion. Therefore, immediately after I bought helium ion microscope, I thought maybe we can use for patterning, atomic layer materials like graphene. So one day I asked my students, could you try to directly mill on the monolayer graphene?
Right.
And 3 hours later, he came back and he patterned exactly as I sketched on the paper. So I was so impressed.
Right.
And then I started to study helium ion beam as a new tool for graphene nanofabrication.
So graphene, as we know, is a hexagonal lattice, and it seemed as though from the images you showed that can knock out just individual atoms almost,
Yes,
and
exactly.
to create defects or
Yes,
or
so
ribbons or whatever you seem to want.
by tuning the dose,
Right.
it's a basically beam current.
Right.
And we can use as a very low damage as a microscope.
Mm-hmm.
And then in the intermediate dose, we can intentionally introduce defects.
Yes.
And then finally, with a very high beam current, we can actually mill,
Mhm.
curve
Yes.
and graphene into the say less than 10 nanometer, structures.
Yeah.
And nice thing is the yield of the patterning
Yes.
is nearly 100%.
Yeah,
Yeah.
it seems like a beautiful tool.
Yes,
And,
exactly.
Do you think that people will be that it'll become more common in the future?
I think so. And at the moment, there are a very limited number of the users worldwide.
Is it extremely expensive, helium?
Yes.
Helium? Yes. So,
Yes,
so
yes, yes.
uh,
I think probably.
compared to electron beam, like a
Well,
Joule
I think
system, for
probably
example.
maybe 3-4 times more expensive.
Wow. Okay,
Yes.
so and joules
Yes.
are already
Exactly.
$1 million or something
Yeah,
like
yes,
that, right?
That's
So,
right.
Okay.
That's right. Yes. Yes.
But at Southampton, who,
Yes.
who manufactured that for you?
It's Carl Zeiss.
I see. It's a Zeiss. It's a Zeiss
Zeiss,
machine.
yes,
I see,
Zeiss
okay.
machine.
All right.
But
fantastic.
recently, we have some domestic, in Japan,
Yes.
and manufacturer,
Yes.
and who are also studying same system
Yes.
as a prototype.
Mhm.
So we are collaborating with that company. It's Hitachi High-Tech Science.
Yes.
Yeah, so we have different the machine which enables not only helium but also the nitrogen beam.
Yeah, I
and
noticed you
also
talked about nitrogen beam today too.
and also we plan to use a hydrogen beam.
Yes.
That would be some interesting extreme.
Uh-huh.
Especially with graphene. Maybe not only milling,
Mhm.
but also we can terminate dangling bonds
Mhm.
Simultaneously with
Mhm.
hydrogen.
Mhm.
So if we hydrogenate graphene
Mhm.
and almost like graphene to graphene, sp2 to sp3.
Yeah.
So we can do some very interesting local modification.
Yeah. Yeah. So as I said this morning, I think that new fabrication techniques and technology are somehow the key that's going to unlock
Yes.
sort of the higher potentials of these types of materials,
I agree.
nanomodular systems. So I think this is
Yes.
a really great step forward. So.
Yes. I hope
Anyway,
so.
congratulations and thank you
No,
again
thank you for your interest,
for letting us tape you here and,
Yes,
and
yes.
for coming to our meeting. Okay.
My pleasure. Thank you
Thanks.
very much.
Thanks so
Thank you.
much.
Keep
Okay.
in touch. Thank you.
Cheers.